Welcome to the deep dive. Today we're diving into a really interesting challenge, something right at the forefront of large language model research.
hmm
How do we make these incredibly powerful models generate text faster, without sacrificing all that quality they've achieved? We've got some great sources looking at some, well, pretty cutting edge techniques.
Exactly. It's a big issue. LLMs are amazing generating really sophisticated text, but the computation needed, the latency, well, it can be pretty substantial.
Right.
So yeah, the research we're digging into looks at strategies to optimize that inference step, mainly by cleverly combining different models.
And our mission today specifically is to unpack this new approach called speculative cascading. It's pitched as combining the best of two other techniques, model cascading and speculative decoding.
That's the idea.
We really want to get into the academic side of things here, focusing on what actually makes this speculative cascading innovative. What's the step forward? Okay, let's get into it. So, model cascading using different size models. That's not totally new, is it? But the paper talks about taking it down to the token level. What does that look like?
Sure. So token level cascading basically takes that core idea using models of different sizes and applies it really granularly, like for every single token being generated.
Ah, okay. Not just once for the whole output.
Exactly. Instead of one decision for the whole sequence, the system checks for each token, should we use the small, fast model, or should we defer to the bigger, maybe more accurate one?
So it's deciding token by token. Dynamically, what makes that decision? There's something called the deferral rule, right?
Yeah, the deferral rule, they call it R, that's key. It's basically a function, it looks at the tokens already generated the prefix and decides use the small model, that's a 0, or defer to the large one, that's a 1, for the very next token.
Okay.
And the paper looks at a few ways to do this. Chow's rule, for instance, that one decides based on how confident the smaller model is. If the little guy seems unsure, maybe defer.
Right. If the quick model is scratching its head, bring in the specialist. Makes sense. And then there are rules tied to cost, like this alpha penalty and loss functions. What's the thinking there?
Well, the rules with a cost penalty try to balance things. Is the potential quality boost from the big model worth the extra compute cost? That alpha parameter kind of sets the bar for when the gain justifies the cost.
Okay, a trade-off.
Exactly. And the loss-based rules, like minimizing 0-1 loss, right versus wrong, or log loss, which penalizes uncertainty, they aim to directly cut down the expected error for the next token. That guides the deferral decision, too.
The paper specifically mentions a diff rule, equation 5. What's unique about that one, especially for these sequential cascades?
Okay, so the diff rule says defer if the top probability the small model gives the next token is way lower by that alpha margin than what we think the large model would give it. But here's the catch for sequential cascades.
Uh-huh.
At the moment you make that call, the big model hasn't actually run yet. You don't know its probability. You're sort of guessing based on how shaky the small model looks.
Ah, I see. So in the purely sequential setup, it's an educated guess about the big model's opinion. Okay, let's pivot then. Speculative decoding sounds like a hardly different way to speed things up. How does that work?
Yeah, it's a different angle. Speculative decoding is more of a two-step dance. First, you have a smaller, faster draft model, split out a potential sequence of, say, the next few tokens.
Okay, a quick guess for a short burst.
Right. Then a larger verify model comes in and checks those drafted tokens one by one. It decides accept or reject.
So small model drafts quickly, big model does quality control. Got it. What makes a token vet accepted or rejected?
There's a specific probability calculation. It's the minimum of one, or the ratio of the larger model's probability for that token divided by the smaller model's probability for that same token.
Okay, unpack that a bit.
Basically, if the larger model thinks the drafted token is way more likely than the smaller model did, paradoxically, it's less likely to be accepted smoothly. It suggests a significant disagreement.
Oh, interesting. So if the small model guess is too far off base, according to the big model, it gets tossed out. What happens then if a token is rejected?
Good question. When a token gets rejected, the system doesn't just stop. It samples a new token, but it samples from a modified distribution.
Modified how?
It's tweaked to favor tokens that the larger model really liked, but the smaller model maybe missed or ranked low. It's like a correction mechanism, trying to nudge the generation back towards what the bigger model prefers.
Huh, that's a neat feedback loop. The paper also talks about lossy speculative decoding. Why would you want it to be lossy? Sounds counterintuitive.
Well, lossy here means introducing a strictness parameter, usually called alpha again, confusingly.
Oh, okay.
This alpha lets you tolerate a bit more deviation from what the verifier model ideally wants. You might accept more drafted tokens, even if they aren't perfectly aligned with the larger model's top choices.
And the benefit is?
Speed. You accept more drafts, you generate faster. The trade-off is that the final output might drift slightly away from what the large model would have produced on its own. It's a controlled compromise.
Okay, speed versus strict faithfulness to the big model. Makes sense. Now, this brings us to the main event, really. Speculative cascading. How does this combine those two ideas we just discussed? This seems to be the core innovation.
It really is. The absolute key idea in speculative cascading is running the larger model in parallel with the smaller model's drafting process.
In parallel. Okay, how does that change things?
Massively. Remember how in sequential cascades, the diff rule had to guess the large model's output?
Yeah, because it hadn't run yet.
Exactly. But with speculative cascading, because the large model is running concurrently, processing the same drafts, you have its probability distribution available right when you need to make the deferral decision for the cascade part.
Ah, so you're not guessing anymore. You have the actual probabilities from both models at the decision point. That overcomes the big limitation of the sequential approach.
Precisely. This parallel computation lets you design much smarter deferral rules, rules that explicitly use information from both the small and large model distributions at that moment. The paper then introduces this concept of a target distribution called pi.
A target distribution.
Yeah, think of it as the ideal distribution you're aiming for with each token. It's basically a mix, a blend of the small model's distribution if you decide not to defer, and the large model's distribution if you do defer. And that blend is guided by these more sophisticated, parallel-informed deferral rules.
Okay, so the speculative cascading means smarter deferral choices because we have simultaneous insights from both models. Now, how do you figure out the best deferral rule in this new setup, the optimal one?
Right? The goal is to find the rule that gets you closest to the true probability distribution of language, ideally, while staying within some kind of cost budget. That budget is usually related to how often drafts get rejected, and this leads to a really important theoretical result, Lemma 3.
Lemma 3. Okay, what's the core idea there?
Lemma 3 basically connects the dots. It says the probability of a drafted token being rejected is proportional to two things multiplied together. First, the probability that you decided to defer based on the history per prefix. Second, the total variation, or TV, distance between the large and small model's probability distributions for that specific next token.
Total variation distance. Remind me, that's basically a way to measure how different two probability distributions are overall.
Exactly. It captures the total difference across all possible outcomes. So intuitively, Lemma 3 says rejection is more likely when 1, the models disagree significantly, high TV distance, and 2, you've actually chosen to defer, meaning the larger model's view is the one you're currently targeting. That disagreement then matters for acceptance.
That makes a lot of sense. More disagreement plus deciding to follow the big model means the small model's draft is more likely to be rejected. So how does this lead to the optimal rule for speculative cascades?
Well, by optimizing that trade-off, mathematically minimizing the loss versus the rejection probability, they derive this optimal deferral rule. It's in equation 10. It essentially says you should defer, set ROPT to 1, if the small model's top probability is less than the large model's top probability minus a specific term.
And that term involves.
It involves that cost parameter, alpha, again, but critically, it also involves the total variation distance between the two models' distributions.
Ah, there it is. That seems like the innovation. The optimal rule for speculative cascading explicitly uses the TV distance, calculated because you have both distributions thanks to the parallel processing.
Precisely. That's a major step. You're not just looking at confidence or simple differences. You're using a formal measure of the divergence between the models to guide the deferral. That wasn't really feasible in the same direct way before. And Lemma 5 then gives the theoretical guarantee a regret bound, showing how close this optimal rule gets to the absolute best possible rule, relating its performance to how good the individual models are.
Okay, so we've talked about deferral rules looking at the history, the prefix. But the paper also mentions token-specific deferral rules. What's different there?
Right. Token-specific rules add another layer of refinement. Instead of just looking at the history, the rule also considers the actual candidate token that the small model just drafted, so the rule becomes RV.
So the decision depends not just on where you are, but also on the specific suggestion the small model made. That sounds like it could be even smarter.
Potentially, yeah. It allows for more fine-grained control. If the small model proposes a token that, even given the history, looks particularly bad or good, the rule can react specifically to that token.
How do you build the target distribution, that point thing, with these token-specific rules?
It's similar in principle. The target distribution, equation 11 shows this. It becomes conditional on both the prefix and the candidate token V. It's still a mix of the small and large model probabilities, but which model you lean towards depends on the rule's decision for that specific token V.
Got it. And then there are these plug-in approximations in equations 13, 14, 15. Why do we need approximations?
Well, the theoretically optimal rules often depend on the true underlying distribution of language, which we obviously don't have.
Right.
So these plug-in approximations are practical heuristics. They use the probabilities from our actual models, the small one q and the large one p, as stand-ins for the true probabilities when making the deferral decision for each token. Equations 13, 14, and 15 just represent slightly different ways of doing that animation.
Okay, different practical recipes. Equation 15 leads to this top alpha set idea. That sounds interesting. What's the logic?
Yeah, equation 15 results in a neat target distribution strategy. For the tokens that the large model thinks are the most likely, this top alpha set, the target distribution, basically just uses the small model's probabilities.
Okay, for the likely ones, trust the small guy.
Kind of, because the big model already agrees they're likely. But for all other tokens, the ones outside that top set, the target distribution becomes a rescaled version of the large model's probabilities. So you use the small model speed for the consensus high probability tokens, but rely on the large model's accuracy for the trickier, less probable ones.
That's a pretty elegant way to allocate resources, balancing speed, and accuracy based on model agreement. Now, the paper connects speculative cascading back to the methods we already discussed using Lemma 2 and Lemma 8. What do those connections tell us?
Good point. Lemma 2 is interesting because it shows that if you set up the target distribution in speculative cascading in a particular way, the whole thing essentially simplifies down to the lossy speculative decoding we talked about earlier.
So speculative cascading is actually a broader framework. It includes lossy speculative decoding as a special case.
Exactly. It shows it's a generalization, not something totally separate. It provides a unifying view.
Okay, that's helpful context. And Lemma 8, what connection does that make?
Lemma 8 links back to that diff rule from the sequential cascades. It demonstrates that under certain specific conditions, basically, as you move towards purely greedy decoding, where parameter t goes to 0, the optimal speculative deferral rule we found actually becomes mathematically identical to the old sequential diff rule.
So in that specific limiting case, they become the same.
Right, which again reinforces the idea that speculative cascading is an evolution. It matches the older method in simple cases, but offers more advanced, beneficial strategies, especially when you're not just doing greedy decoding thanks to that parallel processing.
Okay, so wrapping this up, if you had to boil down the fundamental innovation of speculative cascading, what would it be?
I'd say it's the ability to make much, much more informed deferral decisions. By running both models in parallel, you overcome that core limitation of sequential methods and can design smarter strategies that directly use insights from both models simultaneously.
A key part of that smarter strategy is incorporating the total variation distance into the optimal rule, right? That seems like a big academic step and a practical one for tuning the system.
Absolutely. Using TV distance is a concrete way this framework leverages the parallel information. It quantifies the model disagreement and uses it to actively guide the trade-off. And importantly, the paper backs this up with experiments showing that using models like Gemma and T5 on tasks like summarization, translation, coding, speculative cascades consistently achieved better cost-quality results than the older methods.
Really compelling stuff. It definitely makes you think, with these kinds of improvements happening, what other hybrid strategies might emerge? How else could we potentially combine model strengths to push the boundaries of speed and accuracy for all the different ways we're starting to use these AI models? It's certainly food for thought.
Definitely. The field is moving fast.
Well, thank you for walking us through this deep dive into speculative cascading. Really fascinating.